simple derivative, so I know the derivative is correct.
Right.
It's not even on
Okay,
purpose.
so this is page 275, number 11.
Yeah.
What was the function?
X to the fourth minus 3x cubed plus 2.
Isn't this the least part that I just found?
Okay, so f prime 4x cubed minus 9x squared.
Yep.
Okay, and then if we're looking for zeros, you said your guess was what, 2.8?
The first one on the left side was 0.9.
Oh, okay. How do I erase that?
At first it was 1, and then I saw it went to 1, and I was worried if it screwed something up, but it's actually 1, so.
Okay, so the guess was 0.9.
Yeah.
Alright, so for Newton's method, each x value is the x value before it minus f of x over f prime of x. Is that correct?
Yep.
Alright. So you can either put this into your calculator by hand or do it otherwise. We'll kind of put it by hand this time just for practice. So yes. So we'll store 0.9 as x. So that's our x naught. And then we'll just say x minus.
And this is the one that worked. This one went straight to 1 when I was.
What did
So
you do?
x. No, it wasn't squared, was it? X to the fourth minus 3x.
The next one gave me 48, or whatever it was, like 20 something.
Every time. Okay. Then of course 4x cubed minus 9, yeah, good. X squared. Yes. So that'll give us our next value, but we can also just store it as the next x. And then we do the exact same thing, and the exact same thing, and the exact same thing, and it certainly looks like it's going to 1. And after that, it's just going to keep giving you 1. Yay!
Yeah.
To check your answer, you can put the original equation into y equals and just check it with the trace function.
And then my next x naught was 2.9.
Okay.
And that's when it screwed it up. It eventually settled at 2.91 and a bunch of stuff. But, yeah. Oh! It worked on this for some reason. Which calculator was this on? Not this one.
So there you go.
I guess it works.
So that'll find your 0, which that one's a what looks like a non-ending, non-repeating decimal. So this is basically how you gotta find it. I mean, your trace function will do the exact same thing. That's what your trace function does.
Nah, that's like 2.9.
Right. It is like 2.9.
Yeah.
That's an accurate statement. Okay. Any others you have questions on? By the way, for anyone watching, the homework was, I think I just told you to pick some problems on page 275.
Are you recording?
Yeah.
Oh.
I told you I was recording.
Where?
At the beginning.
Where?
My phone's
I did not.
sitting
I'm
here.
kidding.
I was confused because I didn't think you did that.
Yeah, I wouldn't record without telling you first.
Well,
Whether you pay attention or not, I have no control over that.
When you just said
No,
for
no,
anyone watching, and I was like,
Yes.
And then number
Would it
20
help if I
was
called them chat?
yeah.
Yeah.
Chad. That's actually hilarious.
Oh, this 13-year-old just does it like multiple times a sentence, and it when there's like 4 of us on Discord, and
Oh.
it runs right through me. It gets on my nerves like something
God,
fierce.
that is rage bait. Using chat
Yes.
a lot is rage bait.
Yes. Anyway, moving on. So
That's so funny.
Yeah,
Yeah.
I mean, for 27, it's the absolute value of x squared minus 1.
sure.
I don't
Are you
know
wondering how to
find
do that on
the
here?
derivative of a absolute value. But I know since it's an absolute value, there's going to be points. But also, is there going to be an actual zero within that? Which, if you graph it, there's one peak at 0.
Okay.
Yeah, so...
Good. That's actually a great question.
Yeah.
For one, the first thing that it would be nice to do would be to graph it, but depending on your graphing calculator, obviously these ones, I mean not obviously, but these ones can do it. A lot of them can't. Well, that's not true. Some of them don't have a good way to put absolute values in, and there's a real good chance you don't know how to put them in on these calculators. You
Oh,
figure
yeah,
it out.
I found it out, yeah.
Yeah, but off the top of your head, you might not. So, what you really want to ask yourself, not ask yourself, what you want the ability to do is also to be able to do these by hand. And I don't mean even the whole problem in this case. I mean, so this was what number? 27?
Yeah.
Okay. So f of x was the absolute value of x squared minus 1? Is that right? Yeah?
Yeah.
Okay. I want you to be able to do that by hand. Just like, what values is this actually going to change at? What value will this one change at?
Not gonna lie. I don't even know what an absolute value is, so I just know the question was.
Like where
No, I
any
just
negative
never,
values
like-
go straight to a positive value, no matter what. So like at the absolute value of x, it's just a v. It doesn't go into the negative values.
So basically, yes, anything inside of it, when you take its absolute value, it will be the positive version. So the absolute value of 3 is 3. The absolute value of negative 3 is 3.
Ah, that's all it does?
Right.
So like, will that just be x squared plus 1?
For much of it, no, not x squared plus 1.
Ah.
Never. But for much of it, it will be x squared minus 1,
And then you have to take the absolute value of it.
except where it would be negative. Where will this be negative?
Negative 1.
Where, I'm sorry, I misspoke. Where will x squared minus 1 be negative?
Oh yeah,
Where
that
x
causes
is
negative 1.
When x is 0, it would be negative.
Yeah.
What range, what domain of numbers will it be negative?
Negative 1 to positive 1.
Negative 1 to positive 1, which type of parentheses?
Ah.
Open.
Open parentheses. Yes, so from negative 1 to 1,
Yeah.
on this domain is where that equation is going to end up as negative. So during that domain, so for negative, well, some people would write it this way, some people write it as negative 1 less than x less than 1. Either way, I don't care. But for that happening, then f of x is equal to negative x squared minus 1. Which all that's going to do is make it positive. Right? For everywhere else, then it's just x squared minus 1. So, if your calculator did not do it, you just have to be careful of any values inside of this. But the problem is, these edge cases are also your answers.
Yeah, but they can't be.
In this case, they are. What?
I
What do you mean they
thought
can't be?
I thought there weren't.
So the answer is
For my
negative?
only answer, I put
Oh,
0.
negative 1.
Because that 0, that has the slope of 0. Yeah, I didn't.
Oh wait,
I
sorry.
wasn't-
What was the directions for that section? Oh, critical numbers. So yes, when the slope is. Right.
Or maybe I.
So this isn't a Newton's method problem at all. You're not finding zeros.
What are you finding?
You're finding the maximum, which is when the derivative is zero. Sorry, this is a different section than the one you guys were having troubles with. I thought I didn't actually look at the directions. I just believed what you were saying. My apologies. These are maximums and minimums, so you're looking where the f prime is zero.
I didn't even read the end. I just saw critical numbers and thought it was zero.
Yes.
Whoops.
Yes. Okay. So my apologies.
Well, maximum and minimum is still.
So maximum and minimum here.
You, take the derivative.
So on a lot of them, you can take the derivative. Absolute values tend to have points,
Yeah.
and the derivative at a point is not zero. It's nothing.
Yeah. Exactly. So.
If we do a graph just to kind of get started on this one, which again you can do that two different ways. You could graph both the positive and the negative version and ignore everything that's negative, right? Or you could use the absolute value thing in here, which I believe is under math. Oh, it might be under number. Yeah, absolute value. So absolute value of x squared minus 1 so you have local minimums at -1 and 1. The only problem here is proving that they are a minimum.
Huh.
Which in this way, honestly, the best way to do that is look at where they're going to go at those places. And yes, they're heading more negative, and yet you know they can't be negative, so their limits are zero. This one, for this line, it's 0 from the left. From here, it's 0 from the right. 0 from the left, 0 from the right. So, yes, there are zeros there. 0 is your minimum in this case. You're not looking for zeros. They just happen to be 0.
Okay.
So -1 and 1 are your answers. Because we kind of proved it here. Well, not actually, we didn't actually write anything down. But we said, where would this go negative? And it would go negative there, and that's when it pumps back up. So if the whole function is an absolute value, well, if there are any points in it, that's probably the minimums, and they're probably all zeros as well. If this function would have been, say, +5, now that's all going to change. But since it was all in an absolute value, they're going to be zeros. Or nothing. Like if, for instance, if you take this graph and just translate it upwards by 1, they wouldn't be zeros, there wouldn't be any zeros. So it would still be where there are points. I realize those don't quite look like points,
Yeah.
even though they are.
It's a weird format.
Well, think of what it actually is. X squared minus 1.
It's supposed to make, yeah.
So it is a point, it's just not a very sharp point. Yeah, because that was what I said you could do. Otherwise, is just put in both of these.
I like the Under Armour logo.
Oh, it looks like that.
Yeah, it looks like the Under Armour logo.
And just ignore all the negatives. So I think that might actually be clearer as to what's happening right here.
Oh, and you can see them both
This is
across.
what the Under Armour logo actually means.
This is how they make it.
Yes, it's certainly not just a U and an A together.
Wait,
Under Armour.
what's the... Wait, what?
I thought were joking. Yeah,
No, I didn't
it's
know that.
it's UA
It
for
said
Under
It
Armour.
is a UNMA.
MMA.
Oh jeez.
Well, how was I supposed to see that?
It's literally the only two letters.
That's like the arrow in the FedEx. Like nobody sees that.
I thought it was-
Really?
Until you point it out, though.
Okay.
Okay, well I did know about that one. I can't help it when
Did you see that one? Naturally.
Okay,
Yes.
guys, moving on.
Anyways.
Any other questions here? Yeah, for most of them, you just take the derivative, and obviously that's where the slope is 0.
Yeah.
So it's going to tend to be where there's a maximum or a minimum. It's only where you get where are the other critical points you have to check for maximums and minimums.
Other critical points.
Yes, other than
zero.
horizontals or absolute values.
Maximum. No, never mind.
That's what you're looking for.
Um.
I'll give you a hint. They won't be on 11 through 30, but they will be on 31 through 38. What does 31 through 38 have inherently?
Absolute extreme.
Infinity.
No,
Um.
it has domains.
Oh, wait. Yeah.
So you have to check your A and B. You have to check your two ends of your domain.
Yeah.
Okay.
Because, like in this one, let's say all we had was the red line, right? And you were looking for maximums and minimums, and you were looking for between, say, -2 and 2. The absolute, or it has a minimum at 0, but the maximums would be at -1 or -2 and 2, because it's just that's the highest points in your domain. Make sense?
Yeah.
Weirdly, they tend to call those absolute maxima, because there aren't any other ones in your domain, even though there are other bigger ones outside of your domain. That's what I would call local naturally, so you have to be a little careful.
Yeah.
with
Why
that.
is that not low?
Yeah. It's not local because inside of the domain, you could have more than one. For instance, I'll give you an example.
Oh, so of that domain, that's the absolute.
Right.
Okay. Makes sense.
Will that do it? Let's give that a look. Not enough. Or too much, I should say. So, like, this is still a local maximum,
Yeah.
even though there are bigger maximums if this whole thing were your domain. Your local minimum would actually be wherever this number is here, even though it's not on the screen. Make sense? So your absolute minimum would be whatever that is.
Even though it's not on the screen.
Well, assuming that your domain was the whole width of the screen.
Oh, okay.
Yeah. If it was for, say, -3 to 3 pi, I think each one of these represents pi in that one. X scale, half pi. So if you were going from, say, -2 pi, which is there, to +2 pi, then your absolute minimum would be at -2 pi. Because each line is half of pi on your trig zoom. But yeah, it just gives you an example of multiple local minimums, multiple local maximums, and different absolute maximum and minimum than either of those. And these do tend to be important if it's like a real graph. Those could be where like things tend to stop in a system. If you're dealing with like energy, those could be like where you're losing money. Those could be like whatever. Depends on what your graph's actually representative of in like real life. Math's weird in that it both like over and underestimates the amount of graphs you'll ever see in your life, because it just completely depends on what you do. Like even in business, like some jobs would have a lot of graphs and some will have probably never none, but very few. How many of them will have functions at them inherently? Not a whole lot, but a lot of times you have to set a function equal to it. You have to do a best fit line of it. Which if you want to before the end of the year, tell me, and someday I'll just show you how to set best fit lines to actual data, and it's not hard. Both Excel and Google Sheets can do it.
Then you just get the average of all the points.
Yeah, it'll put a line. It'll actually make up a line that will fit it as best as it can guess out of. And remember, but it's doing it numerically, a numerical estimation. So it's trying it's like getting closer and closer through, and it's like, okay, this is as close as I can get, kind of thing. And then it'll actually give you what's called an R-squared value of how close it actually is. An R-squared value of 1 means that all of your data fits on the line.
Oh, so there could be like outliers.
Yes, an R-squared value of like 0 is like, this is completely random.
So none of them actually hit the line.
Not even that. It's like it's actually random.
Oh, okay.
You can have an R-squared value of like pretty high, and none of them are actually on the line. Only at 1 will they all be on the line, or any of them be on the line. It could be like 0.9 and none of them hit the line. They're all just very, very close, technically. Real world versus like theoretical data. That's just kind of how it goes. Like you're measuring, say you're plotting a roller coaster along a track. Inconsistencies in the surface of the metal will make a difference. Wind patterns on each run will mean each run is very slightly different. An earthquake in like California will change the data for one of the runs. Like not by enough probably to matter, but say Virginia. We don't really get earthquakes in Pittsburgh, but in Virginia there was an earthquake that was felt here from Virginia. Yeah.
Earthquake
A few years
in
back.
Virginia?
Oh, was it Virginia? I thought it was Virginia. Or West Virginia? Something. There was an earthquake not that far from here. That, like, some of the people here felt it and some did not. I did not. I was in a car. Rubber tires and a suspension. I never did happen. Then I think my mother texted me, like, did you feel the earthquake? And I'm like, we don't get earthquakes here. And she was like, well, today we did. I'm like, okay.
Just an earthquake in Myanmar is like a 7.5.
Yeah, that was really bad. Yeah.
Where?
In Myanmar.
Yeah, and I didn't even make the connection because everybody kept saying like Taiwan. And it's like nope.
Well, Thailand.
Thailand.
Is next to
That's
it.
what I meant. Sorry,
Yeah.
but it was just close to Thailand, and since Thailand's a better known country in the States, that's what the news is saying.
Yeah.
But it was actually
it's
Myanmar.
not in Thailand. But Thailand did lose like all of its internet. It already has bad infrastructure.
Right,
So.
but where Thailand had, I think, a couple dozen people die in it.
Really?
Like Myanmar had like better part of 2,000.
Yeah, I bet.
I think it was bad. It was very bad. 7.7s is real high.
Yeah.
That's crazy.
Yeah.
Like 7, almost an
Yeah. By the way, you guys, earlier in the year, you guys wondered when logs would ever be used.
Yeah.
That's one of those scales that's logarithmic.
Richter scale.
Yes, the Richter scale, I believe, is logarithmic. I'm not sure what its base is. It might be 10. So every number is 10 times the intensity of the number before it.
Oh.
So like a Richter of 1 and a Richter of 2, that's like a difference of 10.
So 7's pretty bad.
So 3 would be 1,000 of 1, or 100 of 1, I mean. Yeah, so 7's pretty bad.
Jeez.
I could be wrong. Maybe Richter. Actually, wait. Maybe Richter's the one where they kind of manipulated it so they said like 10 would be absolute destruction, like destroy every building ever.
Yeah.
I can't remember. I think there was one scale that was something like that. I don't know.
I mean,
I'd have to look it
there
up.
has to be a highest point that had to have been made up at some point.
Right, but logarithmic graph can just keep going, but it just keeps getting harder to get higher. which we don't want to get
Yeah.
higher. Like California falling off the country will be a number. Just because there's a lot of people think that it'll eventually happen. Like everything west of the
I mean,
San
it is slightly
Andreas.
moving or whatever. It is.
Well, it's still moving. It's
Yeah.
moving west at like half an inch a year. The whole country is.
Yeah.
Just, yeah. There are people that think that that not only did Atlantis exist, but that's what happened to it, is it got run over by another tectonic plate. So, like, the reason they can't find it is because it literally melted into the mantle of the Earth. It's like, it does not exist.
How would that? How would you like?
Well, the tectonic plates, one can go over another. Anyway, back to the math. So, talking about increasing and decreasing functions, this is section 3.4. So around like 278, 279 is where we are at the moment. We said that an increasing function is a function that is going up as you move to the right, a decreasing function is going down as you move to the right. So then, I think the next thing that I had asked you on Friday was, where would that change? Where would a function change from increasing to decreasing?
It said it's maximum and minimum.
Right. So for instance, in this one, it'd be around right there, there, and there. Yeah, so increasing until here, which we don't know what that point is. You can find that point by doing the things that we said. So, yeah. So then the next question is, how do we tell, without graphing it, what that'll be? Now on this one, it's not that bad, we can see it. But sometimes they're really far off your graphs, or sometimes you don't have a graphic calculator, is, I guess, the idea. But,
That's why finding zeros is useful. 'Cause you can
that's
find-
what tells you what the critical points are, sure.
Yeah.
What would be true when it's an increasing function, though?
The slope will be positive.
Right, so the derivative will be positive.
Oh yeah, that's right.
Yeah. So when the derivative is positive, it is increasing. When the derivative is negative, it's decreasing. Which, effectively, if you... If I could go back to the problem we had before. Didn't actually write down the answer, did I? Just left it on the calculator. So one of them was 2.92, effectively, yeah? So, and I think the other one was 1.
Yeah.
So those were your two answers. So how would you test where that particular function was increasing and decreasing without graphing it? You said it's where the slope is positive or negative, so what would you do?
So plug 2.92 into the original function.
Into the original function, you get how tall that original function is at that point. Does that tell you anything? You said where the slope is positive and negative.
Yeah.
But if you put 2.91, whatever it was, if you put 2.919639566,
Do you put it into the derivative?
if you put that into the derivative, what do you get?
0.
0. Is that going to be
wait,
helpful?
I don't
No.
know.
So where do you want to put it in?
Where you know zeros are?
Yes.
Oh, okay.
But anywhere? No. There are in this particular one, there are 3 places you would check. To the left of 1, in between 1 and 2.9, and to the right of 2.9. Any numbers you choose in those regions, assuming you were right on this. But no, this didn't find the critical points for this.
We found the zeros.
You found the zeros for this function,
Yeah.
which is not what we're talking about.
Who knows?
So, sorry, this is an invalid problem
We could
because I misunderstood what
I
you were
mean, it's
doing.
valid for Newton's method.
It's valid for Newton's method, but not for what the direction said for that problem.
I'm really good at reading directions.
So, just for fun then, and for a review, why don't we do it with this one? Sine of x plus half x.
Oh.
We have our guesses, right?
Okay.
We have some guesses. Let's just do a domain from, say, 0 to 2 pi.
Okay.
Alright? So from 0 to 2 pi, we have a guess of a maximum of, what would you say that is?
1.3.
Well, no, this is half pi. That's pi.
Oh.
So,
3/4 pi.
okay. We'll try 3/4 pi.
I
So,
told you that's right.
this was f of x equals sine x plus 1/2 x.
Yeah, that's something.
And our domain is 0 to 2 pi. Ah. So our guess is going to be, you said 3/4 pi.
Yeah.
But we're looking for its maximums and minimums. So what are we trying to find? Where 1 is 0 this time. Let's do it right this time.
Very better.
Wait, did I say one? Wait, what did I say?
No, what is
Where 1 is 0
I'm gonna type that.
to find extreme points or curved points.
it? Well, the derivative is 0.
Where the derivative is 0. So first we need the derivative. So derivative of sine is cosine.
Yeah.
If that's 1 over what?
2.
Um,
It doesn't look like big deal.
It doesn't look like, I realize that. Okay, and the derivative of 1/2 x is 1/2.
1/2, yeah.
Okay.
And so that is,
wow.
that is the 0.
Well, that's the derivative. We need to find where this is equal to 0.
I see.
So,
Negative 1/2. No.
so if we subtract 1/2 from both sides, we get the cosine
Right.
of x equals negative 1/2. And then what do? This is actually an interesting test to remember if you remember from last year. You should have done it in trig. I know you did it in physics. But we didn't do it quite like this. We did it with tangent a lot, not cosine.
Well,
How do you solve for x?
so here's what you do.
Same thing to both sides. That's your hint.
Oh, you make it 1. You give it 1 on both sides.
What?
Wait, it's the antiderivative.
My function is
Not antiderivative.
No,
What the heck? I can't get
You
this
take
right.
one of both
no,
sides.
What the heck is it called?
Not inverse.
Inverse function.
Inverse, in this case, inverse
cosine.
cosine. Yeah, so it's, well,
Oh wait, cosecant.
no.
Oh no, that's not what that is. That's a different thing.
Yeah, it's just inverse cosine.
You said no, and I was like, oh gosh, yeah, you're right. That's a different thing.
So those effectively cancel each other out over there, and you're left with,
Are you sure it's not cosine of negative 1 pi?
We went over this.
he's,
Oh, he's joking, isn't he?
yes.
I was gonna say, it's like not this again. Please don't do a whole class on why it's not that again.
So the inverse cosine of negative 1/2.
It's probably 7.
Are we in radians? Yes. Inverse cosine, negative 1/2.
It wasn't 7.
You get, that's one value.
What's the other value?
What was our initial value again?
So this is the problem. What did you say? Sorry.
Yeah.
What was our initial value? Not that.
Oh,
It
okay.
was sine.
But if we look at our graph,
It was sine, and then it was 0.5x, right?
Well, you said 3/4 of pi. What is 3/4 of pi? Yeah, exactly. So
7.
7. That's 21 cos.
so you weren't very far off. 2.09 is one of your answers. So what's the problem with doing it like this, though? Do you see it? So we got an answer out of this. Your calculator used Newton's method, because that's what it's using,
Yeah.
to get you whatever it said. 2.094.
Oh, the problem is we need our second value.
We know that there's 2 here. How do you find the second one?
You plug in the other one and.
Into what?
and
We didn't plug in anything to this one.
You,
We just said the inverse cosine of -1/2.
you take.
This has an infinite number of answers.
You do.
How many is it going to give you?
1.
1. This is one of the reasons we still need Newton's method.
Yeah.
Is because we can't do this one in a calculator. We can get one answer. It's even one of the ones in our domain, which is just random chance. Like if we would have said -2 pi to 0, it would have given us an answer not even in our domain.
Yeah, but like that would be dumb.
So we got one answer out of it. We can't keep using it. It won't work. So we will need Newton's method here to find the other places where this is 0.
Okay.
So we need the next derivative,
I was just gonna say we. I was just gonna say.
which is that. Yeah?
Yeah.
Which means Newton's method this time is a little bit tweaked, where each x value will be x naught minus x prime of x over f double prime of x. Because it's the function you're looking at and its derivative, right? The function we're looking at is already a derivative.
Yeah.
So we're looking at the second. Is that clear that there's 2 there?
Yeah.
That's f double prime.
Chad, can you see the second part?
Yeah, looks good to me.
Chad, can we take a poll?
Oh, that is one thing. I can rewrite it. Yeah, which we can just do that. That's not hard. What's your second guess? That is not the right thing.
What are we guessing?
Where this is?
One and
2.6.
That's not even on the scope.
Well, 2.6 is still less than pi.
Oh, I thought you meant 2.6 pi.
What?
I was gonna say 1.
3.
No, 1 and
It's not that critical, guys.
no.
That's like 2.5 pi, right?
No.
No,
2.6.
that's 1.5 pi.
That's right. That's 1.5 pi. So you could just say 1.5 pi. Just that's not going to give you this one. You could say 1.4 pi. That would give you it. 1.3 pi would probably still work. You
Oh,
see
yeah,
what I mean?
1.
Like it just has to be kind of close.
1.4 pi.
Don't try and like
I'm trying too hard.
yeah. Don't effectively waste your time.
Okay.
So if we go
You'll never get it right.
to the main menu or main screen, so you said 2.4
Yeah.
pi.
Not 1.
So I said
Store
2.6.
x, which ends up being about 7.5.
Told you I was right.
Oh wait, sorry, that's not right.
I said 2.6. That's close.
Yeah, I said it was supposed to be 1.4. Because
Oh yeah.
that's 1 pi, that's 1.5 pi.
Why do we
1
keep
point-
saying 2?
We keep saying 2.
Who did that, guys?
It was me.
It's Daniel's fault.
So, oh, ah, whatever. Okay, so x minus, and then we just put in our 2 things. So we had Cosine of x plus 1/2 on the top. And on the bottom, we just had the negative sine of x. Store x. Then you just keep doing it until it stops moving. It stopped moving. By the way, I think both of these answers are kind of dumb. Can you tell me why I don't like them? Why don't these make sense as answers to give in this exact problem?
Because you can't really. That's not really a point.
Well, it's a non-ending, non-repeating decimal, but that happens a lot in math.
Yeah.
But in real life, what is this? What's the unit on this?
Whatever the unit the problem started with.
Well, but look at our equations. Well, that's yeah. So, what is the unit on x if you're taking the sine of it? It's a what? The only thing you ever take the sine of. What type of measurement is this?
Math measurement.
I'll give you a hint.
Wait, okay.
Give me ones that you might take the sine of. Just tell me the
X?
sine of. No, like a number. The sine of what?
3.
Sine of 3 what? Would 3 feet work there? No.
Pi.
Ah, okay. 3 pi what?
R.
Well, it starts with an R.
Radians.
Radians or degrees.
Well, that's what I know.
So which means it's a what? If it's measured in radians or
What's a
degrees,
degree?
if it's measured in radians or degrees,
It's
it's a what type of measurement?
a measurement.
Not length, not
Circle.
time.
Degree.
Circle.
Measure of an angle.
Oh.
Oh, so a degree.
Circle part.
So either degrees or radians. Yeah. So this is a measurement of an angle, and it's a measurement of an angle in radians. How are those usually written?
R.
Why do you keep saying just the letter? It's a word. What's the unit? Nobody writes R.
Radian.
Radian. Yeah.
That was
So, do you ever see 4.2 radians?
Yeah.
No.
No.
What's always there before the word radian?
Oh.
Pi?
Pi.
Yeah.
So if you were actually to give this as an answer, what you would normally do is divide it by pi and say this is 1.33 pi radians as your answer.
Oh.
And your other one, whatever it was way up there, 2 point something, 2.09. Yeah. You divide that by pi as well. And say this is 0.67 pi radians. So those would be your real two answers in this particular case, just because you normally give them in ways that are useful to people.
Why is that one 666666665 and the other one's not 3333334?
So, if you want the real answer,
It will be 3334. It's just not showing.
no,
Oh.
this would never round up.
Oh.
I would guess that both of these actually are, like this is 1 1/3, and this is
1/6.
2
I don't know.
2/3.
2/3, yeah.
But it didn't get this from 2/3. It got it from that other number that was
Yeah.
which was an estimate.
Oh, I see.
So it rounded down because that's not the real number.
Yeah, okay.
We've lost the significance.
Yeah, okay.
We might guess that this is 2/3,
Yeah.
but we don't actually have the significance.
Right.
This is why sig figs are important.
Why would they not?
This is why sig figs are important. And remember I said round at the end of the problem?
Yeah.
Because if we would have rounded that other one off to like 2 digits, who knows what that one would have been when
Yeah.
we just divided it by pi.
Just wrong.
We would just be wrong.
Hmm.
They would be farther off than necessary.
Yeah.
Because remember, your calculator probably does not use 3.14 for pi.
Yeah.
You can actually check in a way. You just say pi plus 1 It does not use 3.14 for pi.
What do you mean?
No, it uses 3.141592654 at least.
Oh, that's what you meant.
Yeah, yeah. Like it doesn't round to 3 sig figs.
Okay.
That's why I just added one so I could check what number it actually uses when you put the pi button.
Why? What happens if you just push pi?
Can you go to the answer and scroll and see?
Well, pi might actually be it. It might give you it. I had a calculator once that when I put pi, it would put pi over here. Just be like,
Oh.
well, thanks. My 89 titanium edition, you had to trick it to give you a rounded off number.
We just have to do pi to decimal. And then,
Right, and you can do that.
then it goes, oh,
Pi
That's-
minus 1 plus 1.
pi.
That would work as well. Though actually, no. In my other calculator, it probably would have given me pi plus 1 as an answer here. I'd have to hit. It had a third button here that was diamond, so that they could have they had 3 things on each key,
Crazy.
and you hit diamond enter would be approximate answer.
Oh, nice.
Yeah. But then its motherboard went bad
Oh.
a couple years ago. So, but that was right before I got all these. So then I just started using the ones you guys use, which I feel like is probably more helpful to you anyway.
Yeah.
Before that, we required that everyone in physics, trig, and calc. Well, actually not physics, but trig and calc, so kind of physics as well, bought their own graphing calculators.
Yeah.
But then we got these, and I was like, this way there's a class set, and I can just program them into everybody's Chromebook.
Yeah.
So that saves everybody like $170. So I thought you guys would like that.
Yay.
Like, we're not trying to make you guys spend money just for fun here. Yeah. And in college, like, depends on what you do. Some of them are using them a lot less.
Yeah.
Like, it used to be if you would go into like science or engineering, and you didn't know how to use a graphic calculator, you were behind the 8 ball.
Yeah.
That's a
Behind
cool
the
term.
8 ball.
Yeah. If you ever have the cue ball stuck behind an 8 ball when you're not on the last
I
shot,
got you.
being stuck behind the 8 ball is like a bad thing.
Right.
It's a tough shot, man.
Yeah.
Yeah, so that.
Hmm.
But now, like if you go to say, I know Grove City because I've had 2 different students tell me this. Actually, more than that now. If you go to Grove City for say engineering, you don't use a graphic calculator ever.
Oh, wow.
You use like math software on the laptop that they give you.
Ah, cool.
Yeah, namely MATLAB.
Ah.
That used to be the math department used one and the engineering department used the other. So engineering students needed both. They learned both MATLAB and Mathematica, which are like the 2 competing giant programs.
Yeah.
Yeah, which that would sting. So now they at least switched to all use the same one.
Yeah.
Yeah, that's just kind of awful. Meanwhile, they can both do the same thing. Okay, so just wanted to make sure we were kind of clear on those. A lot of times, what people will do for complex ones is write a little number line. Because what we did so far on this problem was we just found the zeros. We have about 1 1/3 pi radians and 2/3 pi radians. That's our 2 zeros. That's not the answer to this problem. So, crit. Technically, this isn't right. And what was it? 2 1/3? Is that right?
No.
2
Oh, 1 1/3.
Why do we keep saying 2?
This was 2/3. Ah.
2.7.
So those are our zeros, but we were trying to find where this is increasing and decreasing in our domain. So where do we have to, what do we have to do from here?
plug those into the wait.
Did you finish your sentence? I only heard the first. I heard plug it in, but I didn't hear what you said after that.
No, I didn't finish.
Plug it into what? Plug what into what? We talked about it before we started spelling.
Plug them into the derivative.
Yes. Plug what into the derivative? These values?
Yeah.
Well, if you do that, what numbers are you going to get?
Oh my gosh. Okay, plug values close to them. And
Right, because if we put these into it, we get 0. That's what this is. That's what.
Yeah.
That's what we were finding. Yeah. So we know that like 2/3 pi and 1 1/3 pi are like critical points. Yes?
Yeah.
What we need to do is check to the left, middle, and right of those two critical points, and effectively inside of our domain. That's why I had this number line stop inside. So pick a number that's between 0 and 2/3 pi. No, I'm getting crazy here, man. Just pick any number between 0
1/3.
and 2/3 pi. 1/3 pi, or just 1/3?
1/3 pi.
Just
What?
1/3.
Okay, it doesn't really matter
Look,
because you can use a calculator to do this. Remember, the derivative is cosine of x plus 1/2. So we're just cosine of, what did you say, 1/3 pi?
Yeah.
All right. One.
Plus a half.
That's funny. Yep, cosine of 1/3 pi, I guess, is a half.
Wait, why'd you add half?
Because that's what our derivative is.
Oh, I
Cosine
okay,
x
never
plus
mind.
1/2.
Yeah.
What are the chances it was an exact number? Anyway,
Well, I just
what's
knew
what's the importance of this one? What does it tell us?
It tells us it's positive.
Positive what?
So
Positive slope. Yes, which means the function is, what's the word?
oh,
Means
positive.
going up.
Ascending.
Incline.
Wait,
Means it's increasing.
oh, that's basically what I said.
Yeah. Is it possible that it's still increasing after that?
Yeah.
Technically, yes, it could do like the plateau thing. We kind of know it's not because we've already looked at what this looks like, but we're just using this as an example. So check somewhere in between those two. You might pick pi.
I choose
It's in
pi.
between them.
Yeah, we'll do 3/3 pi, aka pi.
No, what is 3? You know, 3
-1/2. All right. The importance of that is that it is
minus.
negative.
It's
minus.
decreasing.
So
It's descending.
It's
this
descending.
whole area is going down, and then we just have to check anywhere between 1 1/3 pi to 2 pi.
1 and
1 and 2/3.
2/3 pi.
You guys make everything difficult. You could just
It's
put
not,
in like
we did exactly what you asked.
you did. You
If
could have
you
even
said,
just.
if
We
you
both
said
had the
except,
same answer,
if you
too.
said except 1 and 2/3 pi, then we wouldn't do 1 and 2/3.
Well, 1 and
pi.
2/3 is how many thirds?
Huh?
1 and 2/3 is how many thirds?
5.
Oh.
5 thirds. So.
Ah, there's always legal loopholes.
Ah.
Ah, it deleted it.
Whatever.
We should have said that.
That's where I hit insert.
Actually, we'll do 5.1 thirds.
1, so it's ascending again.
Yeah. Because you guys are picking very specific numbers. Yes.
It's ascending. We just know when it's 1 and not.
We don't know anything about this graph at all. We've never seen this graph in our lives.
But yeah, so now you know that it's ascending ever between 0 and 2/3 pi, descending between 2/3 and 1 1/3 pi, and ascending between 1 1/3 pi and 2 pi.
Wow.
So that's the actual answer to this problem. The only question then is, how do you write that?
Yeah, bro.
What? It's ascending between these. It's these.
It-
Just write it out.
you can write a lot of words. You can also say, um,
So chat, this is something you can also say.
what'd you say?
I said so chat, this is also what you can do.
Actually, instead of for, they tend to use on.
Flip and close.
Oh. You haven't given us any homework lately.
No, no, I haven't.
Well, actually, okay, so is our 0 included or not?
No.
No.
Is it going up at 0?
No.
Yeah.
No, that's 0.
Yes, it is.
Is
Before and after.
0. So 0 is a critical point only in that it's the edge of your graph.
Yeah.
But is the derivative 0 there?
No.
No. So we can include 0 on this particular one.
Yeah, included. Why are you always trying to exclude people? Like, for real. That's who is a nice guy.
But that one is not included because at 2/3 pi, the slope is 0.
Yeah.
So we can't include it there.
Um,
Is that logical?
yeah.
Weird symbol effectively means also or and.
Oh yeah. I remember.
Yeah. Non-inclusive. But 2 pi is included.
Yeah.
Sometimes they won't be. Sometimes it will be.
The 2 pies included.
Well, it doesn't change direction there, so it's still
Oh yeah.
it's still going up there.
Right.
Both non-inclusive because the slope is 0 at those two places. So that would be an incorrect statement. So that's a way to actually write the answer. Yeah. So there are reasons to do this mathematically even when you can graph it, because some things don't show up very well in the graph. Like if you get like a little something like, but that's zoomed way out, this will not show up. So you have a maximum minimum. Yeah, exactly, if you zoom out enough. So there are reasons to do it mathematically, trying to solve for 0. Remember, you don't always need Newton's method. You need Newton's method when you can't solve it algebraically. So with like the cosine, we couldn't solve it algebraically. There's just no way to do that. It's impossible. Go for it. So you got to find the hidden bits if you need to. For instance, on page 281, at the top, you can see, zoomed in real far, you can see that is, effectively like this, but one of those where just the center point might have a 0 slope. But if you zoom out and you show it from -10 to 10, like your average graph, it does not look like it goes horizontal. So just one of those things to kind of be careful of, and it's why you want to solve things algebraically when you can. And the equation they're talking about is a polynomial. Where when you take its derivative, it is obvious that it's going to have a 0 at x equals 0 because there's an x in every term, so you can factor one out. And so when you set t equal to 0, x equals 0 is one of your answers. Yeah. So just something to watch out for. So what we've been talking about has some names. Has a name. If you look on page 282, if you're following along at home, hopefully you're looking at home. Page 282, right at the top is Theorem 4.2, the first derivative test. This is one of the biggie ones. The first derivative test is how you tell a lot of this stuff. Suppose f is continuous on your interval a to b, and that there's some number c inside of a to b that's a critical number. Right? Remember that weird looking like pitchfork sideways looking thing is within.
It means included.
Included within, yeah. Or inside of, like C is inside of A to B. So you have 3 points that are true if that's the case. I, or 1, if the derivative is greater than 0 everywhere, A to C, and if it's less than 0 everywhere C to B, remember C is in between A and B, then f of C is a local maximum. In other words, if it's going up to the left of a critical point and down on the right of a critical point, then that critical point is a maximum. That should make sense, yes? Mm-hmm. Number 2 is the exact same thing for minimums, like backwards. If it's going down to the left of a critical point and up on the right of a critical point, then that critical point is minimum. When I say critical point, I mean somewhere the slope is 0, so which is a particular type of critical point. And then the third one is, well, if it's going up to the left and to the right, or down to the left and to the right, then it's not a extremum. Right? It's like that one right there. That's not an extremum, even though that is a critical point. You want to think?
Huh? Oh, sure.
You sick now?
I was just
Yeah, that cost needs to be taking people a while to get rid of.
Parker said he had it for a month.
Yeah.
After he said.
Yep. That was me last year. I had something that gave me that. It was at least a month. Yeah. So if you can't find the extrema exactly, you just use Newton's method or something like that to find it approximately. If there's only one of them, then something like an inverse function might do that, but realize it's doing Newton's method inside of itself.
Newton was cool. Smart.
Yeah.
Do you think he was the smartest person ever?
I mean, so you're trying to classify an individual type of intelligence, not intelligence overall. Like I want to say that a physicist was the smartest person ever, but that's just, that's my bent in mental gymnastics. Whereas, like, other people might say one of the best writers in the world was the smartest person ever.
No.
Other people would just say Jesus, because Jesus is always the answer.
That's also a dumb answer. What? They're all dumb answers.
But you see what I mean? Like, smart how? There's a lot of different types of smart.
And the ways that count. He was like.
If you mean, or you could mean gives us the most new information into our daily lexicon of, like, not lexicon, daily, like, store of knowledge. Like, Newton definitely did a lot of that.
Yeah.
But did he do the most? I don't know. I mean, then you get people that you assume are the smartest person at least alive, and then you ask them questions and they might give you different answers than you think. For instance, if someone asked Einstein what it felt like to be the smartest person alive, and his answer pretty famously was, I don't know, you should go ask Nikola Tesla. Which just is a banger of an answer. Like, what are you gonna say? Like, pretty good. I am the smartest man alive.
What if Tesla said, pretty good, you should go ask.
Nikola Tesla may have just said, not very good. He
No.
later in life he was not doing so great.
Yeah.
In any case, we're gonna wrap this up, but on page 284, so yeah, pick one or two out of each of the three sections between 11 and 34, and try 'em.
One or two from each section.
Yeah,
Couple things.
one or two. Yeah, like if you're like, this is super easy, maybe just one from that section.
Yeah.
It's up to you. Like, if you haven't noticed, the further you go in this class, the more I'm trying to give you your own responsibility in doing what you need to do.
Yeah.
Because, yeah.
I'll just do two.
Not that you won't get very specific homework in college, you will,
Yeah.
but in many of your classes, they'll never check to see if you did it. I mean, some of them
Because
they
that's what the
collected or
test is
whatever,
for.
but yeah, yeah.
It's also just a lot more work for a teacher.
Or their TA,
Well, yeah.
more likely, if they have one. Anyway, I'm gonna stop this recording. Bye.